Welcome back. Chapter 5. We're going to just pick up 3 quick sections in Chapter 5. Now we're interested in actually comparing samples. We see this all the time in advertisement, maybe Geico versus Progressive. They claim that they can save you over $50 more or save you over 4% more. You cannot just say these things. They have to come from statistics. And so what we'll be doing is looking at one hypothesis testing for these things, and we'll get into some confidence intervals as well. As it turns out, confidence intervals and hypothesis testing, they're not completely different objects. They're kind of similar. But let's go ahead and get started. So we look at maybe on a campus, UCLA, we're looking at textbooks. And we like to compare just to see, are they cheaper at the actual bookstore or are they cheaper online? Maybe at Amazon. So we'll do this kind of quick basic kind of analysis. So maybe we look at the product key, we make sure they're the same book, same edition, and we match them up. For the first book, same edition, same author, everything, maybe it's $47.99 at UCLA new, and at Amazon new, maybe it's $44.99. So the difference would be UCLA minus the Amazon to give us $3 of difference. So this would be our first book that we had done. Maybe the next one is $132. And maybe this time Amazon's a little bit pricier. Maybe it's $135. This one would be -3 because you're just taking UCLA minus the Amazon. Well, point being, you can have a lot of these, and this is a comparing of two means. Essentially, is what we're going to be doing. Again, this is just UCLA price minus the Amazon. This is our difference. So ultimately, when we do go to test these things, we'd like there to be no difference if they're the same, and if there is a difference, if it's not 0 or significantly different from 0, then we can say that yes, there is enough information to say that they are different. So we're given that maybe we did 73 of these things, and what we found was n difference. We had 73 of these things. In this simple case where we have two samples and we're just going to subtract them, and we look at the average of these things, you see that this is just one-dimensional, just one variable, like we've done before. What we do is we notate everything with a subscript of diff, so we see that it's different. So we're told that the total number is n, and x bar, since we're talking about just these ones here, we'll notate it with diff, just so that we can see that, yes, we are comparing two different samples. We come up with 12.76, and the last thing is we also come up with the standard deviation. Standard deviation diff is 14.26. We have all this information, and we'd like to use it to kind of do a hypothesis test to see if these things are different. Now, the way we'll kind of do this is we're using x bar diff to estimate the population mean, but we don't want to do this because it looks like it's coming from one sample. It really is kind of one sample, but the subtraction of two samples to get the one sample. So the population parameter is this mu diff. So if I go to do my hypothesis, I'm testing to see, is there any significant difference between UCLA and Amazon? So in order to do this, we're going to be using the population parameter, which here is mu diff. Mu diff equals, and mu diff something else. Okay, so if they don't differ at all, and again, we're just doing UCLA minus Amazon for our difference. If they don't differ at all, it's going to be 0. So we want to indicate that. Well, there could be no difference, could be 0. And the other option is, well, they could differ. It might not be 0. So we'll go ahead and put not equal to 0. So this is our hypothesis. Now, as it turns out, all the other stuff is the same. You can have the standard error or the standard deviation of x bar diff. It's the same thing that we've done before. It's still just, or mu diff, it's still just going to be, let's use mu diff. It's still going to be this sort of thing all over the square root of n. So you should recognize this formula. The only difference here is, well, we've got these diffs on all of them. Other than that, it's the same exact thing as when we were just dealing with x bar. And it should make sense. We just have one kind of sample here. We'll get into some more complicated stuff in about 5 or 10 minutes. But for now, we'll stick with this. We've got our hypothesis. Let's go ahead and carry this out. So we'll go ahead and find our p-value and all that stuff. So we do need our test statistic. So our test stat is still z. It equals our let's see, our observed minus the null value all over the standard error here. So maybe, let me just write this a little bit different. Let's go with our point estimate. That way I can be a little more consistent. All over the standard error of the point estimate. So forget about that. So our point estimate here is our x bar diff, right? X bar diff. Subtracting off the null value, well, the null value here is 0. We look up to our null hypothesis, we find the HO, we see it's 0. So we want to subtract that off. And then divided by the standard error of the point estimate, which is really the standard error of x bar diff. So if I plug these things in, looking back on our other information, our x bar diff was 12.76 minus 0, all divided by the standard error, which is going to be this 14.26, divided by the square root of n, in this case, is 73. So going through this process, let's do 14.26 divided by the square root of 73. And we get 1.669. So we really have 12.76 divided by that answer. And we get 7.645. Okay, so this is what we've got right now. Get some new paper here. So we'd like to find the p-value on this. We can see that this is a two-sided test. So it means that if I were to draw this thing out, yes, I can miss it on both sides. So somewhere out here is 7.645. I'm looking for the area on the right side. I can also miss it on the left side, negative 7.645. I can miss it on the left side. So this is, the p-value is going to be two-tailed here. So what you would want to do is look up the p-value for negative 7.645. And I believe when you go to your back of the book, to actually look this thing up, you'll see that there are no values that small or that large. And there's this sort of asterisk here for z's that are less than negative 3.5. The probability is less than or equal to 0.0002. So let's go ahead and just use that for now. So that means that this is less than 0.0002, and so is that. Right? This is also less than 0.0002. So the p-value is actually less than 0.0004 when I add these two together. Again, this is two-sided, so I just add them two together, or I multiply one of these by 2, either way you want to think about it. So our p-value is small. So what we can say is, yes, we'll reject HO. I didn't tell you what my confidence level is, but, for instance, my confidence level was 95%. This is very small, less than that. P-values, even if it was 99% confidence level, it's going to be less than that. So for 99.95% confidence level, we're going to reject HO. So we're almost always going to reject HO. So what does that mean? Our HO was that they're different, that the means are different. So what we can conclude is that UCLA and Amazon books differ in price. Now it's really, really tempting to go ahead and say, well, if you look at some of the values, well, that must mean that, UCLA is more expensive. We can't really say that. We'd have to set up our hypothesis different. If we wanted to test to see if one was cheaper, then we'd do a one-sided test. And so we'd have maybe less than 0 or test that it's greater than 0. I guess in this case we'd test that it's greater than 0 if we're saying that UCLA is greater. But because we said not equal, we were just testing for any difference at all. So our conclusion, the best we can say, is that yes, we can conclude that they do differ in price. So do be careful on that. We can also do confidence intervals with these things. So let's do a 95% confidence interval. For the average price difference, UCLA minus Amazon. Now, of course, your confidence level is, or confidence interval is just your point estimate, just like before, plus or minus Z star of alpha over 2 times the standard error of your point estimate. So our point estimate, if we look back, it was 12.76. This was our X bar diff, right? Plus or minus Z star of alpha over 2. Well, again, if you remember, 95% Z of alpha over 2 is 1.96. It's just a good one to go ahead and memorize. That and 90% and 99%. And then we've also got the standard error of this point estimate, which is going to look like this, where we've got the standard error of X bar diff is going to be this sort of thing, all divided by the square root of n, which was 80. Wait, look back. It was 73. So plugging all this in, 12.76 plus or minus 1.96, and we had 14.26 was our standard deviation. It looks like what we should come up with is 12.76 plus or minus 1.96 times 1.67, and when you carry this out, you multiply these two together first, add it to 12.76, and you multiply these two first, and then do 12.76 minus that answer. So if you subtract them, you should get 9.487, and if you add them, you should get 16.033. So this is the confidence level, or confidence interval, for the difference of prices UCLA and Amazon, written this way, UCLA minus Amazon. And again, we said that it's not very different, at least with the two-sided test. They're the exact same thing. They are different for one-sided test. But if you have a two-sided test, and which is what we had, equal to 0 or not equal to 0, what we can do is look for 0 in here. 0 is not in this interval. It's between 9.487 and 6.033. So because 0 is not in this interval, we can say that yes, at 95% confidence, because it's not in here, we're 95% sure that they're not equal to each other. Let's do another quick example. Let's say we were doing some temperature differences. So we're testing the difference in temperatures. And we do 64 for each year. We find that X bar of 2009 is 70.43, and X bar for 2012 is 71.01. Now, the way you would have to do this is you would have to go ahead and make sure that they are the same exact days. So if you're testing February 1st in 2009, you want to test the temperature, use that temperature February 1st in 2012. Generally speaking, if you're doing this, you would probably go ahead and use all of them. So 364, 365, hopefully one's not a leap year. So let's go ahead and look at this. We see that X bar diff, we're going to just go ahead and subtract these two. Where we're doing 2012 minus 2009. This is just going to be just this minus that. So 71.01 minus 70.43 will give us 0.58. So we've got this sort of thing. And we're told that the difference is at a standard deviation of 3.02 degrees. Has the temperature changed? Okay, so we'll go ahead and do one more hypothesis test real quick. HA. We are comparing two different samples now, one from one year and one from the other year. So we are going to be doing the means here. Notice that we only have one standard deviation here. That's going to be important later. So we have one standard deviation. We are doing this mu diff and mu diff. Again, this is just a population parameter. So it could be equal to 0 if there is no change. And if there is a change, then it's not equal to 0. Again, we're not saying that, well, this sample is higher, so because there's, let's go ahead and test that it's higher. We're just saying that it's changed. It would be a different test if we did the other. So let's go ahead and find the p-value. But before we can find the p-value, we do have to find the test statistic. So again, the test statistic is the point estimate minus the null value all over the standard error of the point estimate. So the point estimate here is this X bar diff. It's this 0.58. The null value, we look at our null hypothesis, it's 0. So minus 0, all divided by the standard error of the point estimate. So again, we have this X bar. So we're actually using this sort of thing, sigma over the square root of n, which in this case is 64. I suppose we can go ahead and replace this standard deviation with 3.02. And let's go ahead and calculate what this thing is. We do the bottom first, 3.02 divided by the square root of 64. It's going to give us 0.3775. 0.58 divided by 0.3775 does give us our point estimate, our test statistic, 1.536. Let's go ahead and round that to the nearest hundredth. 1.54, because of course we on our tables only have these things rounded to the nearest hundred. So the next step in their hypothesis is go ahead and find the p-value. This is two-sided, so we're going to go ahead and find this sort of thing, and we're going to look up the area and multiply by 2. So drawing this thing, again I'm looking for this area to the right of 1.54 and the area shaded to the left of 1.54. Let's see, I'll have to go ahead and open up my book. Let's see what it has to say. Negative 1.54, 0, 1, 2, 3, 4. Tells us this is 0.0618. So is this 0.0618. So the total p-value is 0.1236. So suppose we're testing at 95% confidence level. That means our significance level is 0.05, 0.91 minus 0.95, and so we can see that our p-value is large. P-value is much larger than our alpha, which is 0.05. So we fail to reject. And again, what that means is because we fail to reject, it means we cannot conclude that they are different. So we have failed at 95% confidence to show that there is a significant difference between the temperatures in 2009 and 2012. Let's move along. The next that we'll get into is instead of going item by item or day by day, making sure they match up and subtracting each individual one, sometimes we can just kind of look at the statistics from the one and the statistics from the other, and then we can do a direct comparison this way. So let's say we have some race times. We've got men, we've got women. X bar, go ahead and use F and N. Here's what we got. The men run it in about 88.08. The women run it in about 96.28, with standard deviation of 15.74 and 13.66 respectively. We've had 100 men and 80 women. And this is in the same race. So notice now we've actually got two standard deviations. As a nice kind of easy check, if you've got one standard deviation, then we're going to be doing this sort of confidence interval, or we're going to be doing the test just like the previous two examples. However, now that we have two standard deviations, we're not necessarily comparing two of the same levels here. We're not looking at the same day. We're not looking at the same product here. Here we've got one man and we've got one woman. They're completely different, right? So these are actually independent. The last way we might say we were looking at dependent samples. But the easiest way to differentiate between the two is if you have one standard deviation, then you're going to be using the other formulas. If you have two standard deviations, it's going to change just a little bit. So let's go ahead and say we're looking at X bar men minus X bar women. We're doing this kind of comparison. If I want to look at the standard error of this thing, standard error of X bar, I'll write the general form first and then explain it. So the standard error of this point estimate, the point estimate here is, it looks a lot like mu diff. This is going to estimate mu men minus mu women. So it looks a lot like what we've seen before. However, the standard error looks very different. But if you notice, if I take the square root of the top and the square root of the bottom, I'd have s over the square root of n, which is what we used in all of our previous examples or previous problems. And same thing here, I'd have square root of s2, or square root of s2 squared was s2 over the square root of n2. So this is sort of an average, or sort of an averaging of these two samples. So shouldn't be too bad to remember if you think about it like that. We have sort of a similar thing once we get the proportions. It's going to be a similar formula just like this. So if you do recall, yeah, it's compare it to s over the square root of n. It's not very different, right? You square the top, square the bottom. That's the variance for this thing, and that's the variance for this thing. So we add them up and take the square root. We're not going to get into why we do this or anything like that, but that's just the formula that we're going to use. Everything else is going to be exactly identical in process at least. So let's go ahead and use this information, this data here. Let's test if the men and the women ran the same times or different times at 95% confidence. So we set up the hypothesis. This time, just to differentiate, because we've actually got two standard deviations, when we do this point estimate, we're going to use our point estimate as mu men minus mu women. So it's going to actually look like this. If you want, you can shorthand it, maybe M for women, M for men and W for women. Same thing applies though. If they're not different, then it's 0. In the alternative hypothesis, again, we have the same population parameter. We want to see if they're not different, if they differ. So I don't care which one's bigger than the other, just that they differ. So this would be how we would set up this hypothesis. Moving on, let's go ahead and find our test statistic. Works the same way. We have our point estimate minus our null value, all divided by the standard error of our point estimate. So the point estimate is quite simple. It's just going to be, we're doing men minus women. So here we're going to do men minus women. That's our point estimate. The point estimate is x bar men minus x bar women. Our null hypothesis is going to be 0. Right? What's true underneath the null hypothesis equals 0. And over here, down here, standard error of the point estimate. This is kind of ugly looking thing. Sort of an average of the variances. So we have the standard deviation for men, square it, divided by the number of men, plus the standard deviation of women, square it, all over the number of women. And then this is the whole square root of this thing. So this is getting pretty large pretty quick. Let's go ahead and use some of these values in here. So I do have up here x bar m was 88.08 minus 96.28 for the women. And then this is going to be subtract 0, but I won't write that because it's just subtract 0. See if I can't squeeze this in. The standard deviation for the men was 15.74 I'd like to square that and divide it by the number of men, which is 100 here. And then plus the standard deviation of women was 13.66. I'd like to square it and divide by the number of women, which we saw was 80 here. So yes, it does look kind of ugly, but with practice it goes quicker than you might think. So let's see, the top is easy, 88.08 minus 96.28. You get negative 8.2. And on the bottom, let's see, you should come up with, make sure you do follow your order of operations inside here. We want to make sure this is really 247.7476 divided by 100. So I'll do it in 2 steps just to make sure we're on the right page. So it would be the square root of 2.477 plus the other one is 13.66 squared divided by 80 gives me 2.33. So still continuing on, we're looking for a z, right, our test statistic. Plus 2.477. So we're taking the square root of 4.8 here. If you want, you can round to 4.8. So negative 8.2 divided by the square root of 4.81 gives us negative 3.74 rounded to 2 decimals. So we've got our test statistic. Let's go ahead and find the p-value. So again, this is two-sided, right? So I've got 2 shaded regions. I've got negative 3.74 and I've got 3.74. Let's go ahead and look in our book, see if this works. I think if you look in your book, you'll see that, again, this is too small of a value. It's not going to list anything to it. It's just going to say at the very bottom that this is less than 0.0002. Same thing for this, less than 0.0002. So the p-value is less than 0.0004. So again, this is a very, very small p-value, and at 95% confidence, we can see that, yes, our p-value is much less than our significance level, which is 0.05, 0.0004. So we reject HO. So we conclude that we can reject HO, that yes, the men and women do run different times. Let's see. Let's go ahead and find maybe a confidence interval for something similar to this. So let's find the 95% confidence interval for the difference in birth weight of smokers and non-smokers. Okay, so we're gonna go ahead and be given some birth weights here. 6.78, 1.43, 50. Fill this stuff in, and 100. And okay, so we're asked to go ahead and look at this thing, and maybe we suspect that, yeah, there's a difference with birth weights. So what we like to do is we like to go ahead and find a confidence interval for the difference in birth weights. So let's find an interval here. Let's do an interval for mu of non-smoker minus mu of smoker. And again, we're going to be using this second type of formula because we have two standard deviations. Another way to think about it is we had one standard deviation for the other one, but if you look, the standard deviation was for the difference. So that would be why we use standard deviation S diff or sigma diff, depending on what we're doing. And here we've got two standard deviations, one for the smoker birth weight and one for the non-smoker birth weight. So this tells us we're doing the second kind. So let's go ahead and find the standard error of this thing. The standard error of X bar non-smoker minus X bar smoker. So first things first, we want the standard deviation. We're going to go ahead and plug in for the non-smoker. 1.6. We're going to square it and divide by the sample size here of non-smokers. We have 100 of them. And we're going to go ahead and find the standard deviation of the smokers, just 1.43. We'll square that and divide by the number of them. Let's go ahead and find this out. 1.6 squared divided by 100 plus 1.43 squared divided by 50. So this is going to be equal to the square root of 0.0665 or thereabouts, which should give us about 0.258. So we're asked to find this confidence interval. So remember, a confidence interval is nothing more than the point estimate plus or minus z star of alpha over 2 times the standard error of the point estimate. So here our point estimate is going to be X bar of, what do we have, non-smoker minus X bar smoker plus or minus z star of alpha over 2, which is 0.05 over 2, and the standard error of X bar non-smoker minus the weight of minus average weight of the smoker's baby. Okay, so filling this stuff in, non-smoker minus smoker baby, we do get yeah, I guess that's 0.4. So we get 0.4 plus or minus, we're doing a 95% confidence, and the z star of alpha over 2 when we're doing 95% confidence is 1.96. The standard error of this thing we just found on the previous page. So normally you would go ahead and put this big ugly mess in there, and what we got was 0.258. So I'm going to multiply this by 0.258. So we got 0.4 plus or minus 0.506, and so we got 0.4 minus 0.506 gives us negative 0.106, and 0.4 plus 0.506 gives us 0.906. So this is our confidence interval. What we notice about this is that 0 is actually inside of here. We have negative to positive, so yeah, 0 is actually in here. So at 95% confidence, it would not be possible to conclude that they are different, right? It's possible that they're different because 0 means that they're not different, and in this interval, it's in there. So we cannot conclude they are different. Now, very, very briefly, let's get on to the topic of proportions. So we had just kind of broached the subject in this last lecture or two. Proportions, again, we're going to go ahead and call p hat this point estimate, and it's going to estimate our population parameter. What p hat actually is, it's just the number of successes over the total number. So this looks very similar to stuff that we've already seen. Now we're actually going to get into the standard error. So the standard error of p hat is going to be this. It's going to be the square root of p times q divided by n. And again, q here is just equal to 1 minus p. So just like before, q is the probability of failure, is the complement of p. It's the same sort of idea. So far we've got this is our point estimate. Right, this is our point estimate. And this is our standard error, which is really all we need for our hypothesis or for our confidence intervals. So again, so your confidence intervals are just your point estimate. So it's just p hat plus or minus v star of alpha over 2 times the standard error of p hat. So in this case, it's actually going to look like this, pq divided by n. And as far as for your test statistic, you'll have the point estimate minus the null value, all divided by the standard error, again, of the point estimate. So you'd have point estimate, your p hat, minus your null value, all over this ugly thing. So just kind of foreshadowing. Next week, when we do continue this, we'll look at comparing two different proportions from two different samples. So we saw when we compared two different means from two different samples, it was sort of the average of the variance. So what you'll see in this next lecture after this is this sort of ugly, it looks ugly at first, but it's just the same kind of average of variances. If you want, you can flip ahead. Also worth noting, a lot of this is kind of some new terminology, but you'll see that in Chapter 6, we'll do the same exact things, and we'll repeat everything that we've done in Chapter 4 and 5, only instead of using standard normal random variables, which are z, we use our studentized variables, which are t. So it's just as simple as, in Chapter 6, instead of using this z star alpha over 2 for everything, we use t star alpha over 2. So it's small change there. So if you can get this stuff now, you're really studying for two tests at the same time. Let me go ahead and show you one more thing that can happen. Suppose we're looking at the margin of error. The margin of error is just coming from the confidence interval. The margin of error here is v star alpha over 2 times the square root of PQ divided by N. So like before, we can go ahead and say, if I have an idea of what P is, have an idea of what Q is, I can go ahead and find out how large my sample size needs to be at certain confidence interval. So maybe we're looking at sample size again. Now your book does not give the final formula. It just kind of starts like this and tells you to work through it. I'm going to go ahead and just work through it and just tell you to go ahead and write down the formula. It'll be much simpler. So what we end up doing is we take this thing, we divide it out, margin of error, divided by z prime of alpha over 2 equals the square root of PQ over N. And I'm going to square both sides. So I'll have margin of error over z star of alpha over 2 is equal to PQ over N. And with a little bit of rearranging, I'm not sure how you might rearrange this. Some of you might write this as N times ME, margin of error, is equal to PQ times Z star of alpha over 2. And at the end of the day, wait a minute, I missed the square. Should be squared. And so should this be. Sorry. So go ahead and let's change that. Good. I think now we're all good. And so N is really equal to PQ times Z star of alpha over 2 divided by the margin of error squared. So this is your basic easy formula to use. So say I'm looking for a poll, or I have a candidate in some kind of election, and I've estimated that the rate of approval is about 40%. And I want to see, okay, how much do I have to sample? So I'd like a margin of error to be within 1%. So that seems pretty standard. Margin of error within 1% at 95% confidence. So I'd like to see the sample size here. Namely, the smallest size that I can guarantee that my estimate is within this size. So here's what we have. We've got P is 0.4, so that means Q is 1 minus 0.4 is 0.6. So my N is 0.4 times 0.6. Z star of alpha over 2. This is 95% confidence. This is 1.96. All divided by the margin of error, which is 0.01. Squared. I should also mention, sometimes they might say a 1% error. So if they say 1% error, we really know that proportions are just like percents. So if I said 40% approval rate, I'm writing P as 0.4 and Q as 0.6. If I say an error rate of 1%, I really mean margin of error of 0.01. Okay, let's go ahead and put this together. So 1.96 divided by 0.01 is 196. Square it, and then times 0.4 times 0.6. So I have N is equal to 9,219.84. Of course, the same thing applies. We have sample size. We cannot pull a fraction of a person, so I'm going to round up. It has nothing to do with this 8, just the fact that I have to pull an extra person to guarantee this. If it was 0.14, I would still round up. So I need 9,220. Now suppose I have the same idea. A lot of times we don't have an idea of the population parameter. I won't normally know what the rate of approval is of my candidate is. So if I don't have these P and I don't have this Q for the population, what you then do is you use P is equal to 0.5 and you use Q is equal to 0.5. So suppose we did not have this, so just hypothetically, same idea, we do not have this, then the new kind of equation becomes n is equal to 0.5 times 0.5, and again 1.96 is still coming from the same place, and 0.01 is still coming from the same place. 1.96 divided by 0.01, square it, and then times 0.5 times 0.5. We actually get 9,604. So here, there's no decimal at all. I didn't have to round at all, so I'm going to leave that as is. It's the only time I don't round up. So this is when P and Q are given or known. No P or Q given or known. If you're wondering why we use 0.5, it's not really an average. It's more so just being conservative. When you look at this original formula, we've got this P times Q. Well, the smallest or the largest this can be, because again we have P times 1 minus P, the largest that can be, being that these are complements, is 0.5 times 0.5. If it's any other number, it's actually going to be smaller. So you can kind of confirm that 0.4 times 0.6 gives you 0.24, and 0.5 times 0.5 gives you 0.25. It's the largest that it possibly can be. So this is really a conservative approach. So we've looked at proportions. Just basically, you can do the same thing, confidence intervals, using this error formula, the point estimate. And eventually we'll get into these hypothesis tests as well. And you should also, if you haven't already done so, might want to write down this formula for the sample size of proportions. Note that if P and Q are not given, we'll use 0.5 here. Otherwise, we'll go ahead and fill those in. All right, well, thank you very much, and good luck. I'll see you next week.